Hi guys, nice to see you back. The goal is to start playing with our digits, to make numbers. But the last step before reaching that level is here. So if you just watch this digit, I can modify its brightness. Where the brightness for this digit is relevant is because that's how you understand how to size the limiting resistor for the LEDs. And also, some integrated circuits called decoders, which are controlling the 7-segment displays, are having a limited maximum amperage to deliver, so you should be able to control the amount of amperage and to not forget about the consumption. If you energize all your project from a battery, then it's important that the consumption to be just low enough to limit the consumption and at the same time to still have a very visible LED or digit. So let's start it. Last time we built a simple testing circuit where the key was right here, a limiting resistor inserted in series on the wire. So the purpose was just to check the polarity of the LED, because if you connect it opposite way, nothing is going to happen. And to also check if the LED was functional, because this one is, but this one is defective. Okay, either way you connect it, the light won't go up. So this is defective. This was the tester last time. Today we're going to build more advanced testers. Let's consider them semi-professional ones, where we're going to be able to play with the brightness. And right before we start it, you can clearly see I can go for this LED, for the red one, from a minimum to a very bright appearance. Okay, and I can do the same for the other two ones, see? So let's find out what is the diagram we're going to use for that. I'm gonna make it here first. Here we're going to have our power supply, positive in the top, 9 volts. This is gonna be resistor R1, R2. This is going to be a potentiometer, P1. Right here we're going to place a Zener diode, D1, 4.7 volt, 4.7 kilo ohm here. The original diagram was having 330 kilo ohms. I modified this to 220 kilo ohms. Here the potentiometer is going to be 100 kilo ohms. And we're going to connect this on an operational amplifier. This is the non-inverting input. This is the inverting input. Here we're going to have the ground, which is the pin 4. No, inverting input is pin 2, non-inverting pin 3 is a classical operational amplifier. Here we have the pin 7 for the positive voltage. Here we're going to have a special pin 8, which is for the bias. When this pin is connected to the power supply, the consumption of the integrated circuits goes very low, and this is our interest. And then we use the output of this operational amplifier, and we're going to connect it to a NPN transistor. Okay, so here we have R1, R2, it's gonna be R3, 22 kiloohms, R4, 10 kiloohms. That's more important. This is R5. I'm going to call this a current sensing resistor. Current sensing resistor. And this is going to be connected over here. This is our feedback line. So exactly from here, the current is going to be sensed and sent back to the inverting input of the operational amplifier. Right here we're going to have, I'm going to explain you why, two Zener diodes in series. And across these two Zener diodes, we're going to have our LEDs we want to check and select. One here and another one right here, right across the Zener diodes. So LEDs to pair or select. Okay. So far so good. The resistor R5 is about 50 ohms, not kiloohms, right? 50 ohms. Now the components. This integrated circuit is an operational amplifier, TLC 271 CP. The transistor to N2222 for the American system. An equivalent for it is BC337 in the European system, but we can find both kind of transistors everywhere. Very good. So the diodes D1, D2, D3, all of them are 4.7 volt. 4.7 volt. Okay. Now for the integrated circuit, when you are going to connect it, if I'm going to draw it quickly here, view from the top, this is TLC271 we're going to use. It's actually right here, this little black guy. According to the notch, we have the 8 pins. We count counterclockwise. Pin 1 is right below the notch. 2, 3, 4, 5, 6, 7, and 8. So here, pin number 1 and 5, which are the compensation, they are not in use. This is why you couldn't find them anywhere around. So we only use the other pins, but not these ones. Very easy. If you go on abra.com, remember abra.com is a company having a location in Montreal area and another one in the New York State. So if you order it on the Canadian site or on the American site, you're going to find these components. That's a very cheap one here. It's something around 1.2 Canadian dollars. The transistor itself is something like 75 cents. You're going to find easily this one or that one of them for sure. The Zener diodes are something like 15, 16 cents each, so peanuts. With a couple of bucks you can build this diagram. So now, just a couple of words about the diagram very quickly. The two inputs of the operational amplifier, they compare the values of the voltage coming here. They amplify the difference, so this is converted into a current by our transistor, which is able to sustain the current through our LEDs And the current sensing resistor, which is in series with the collector emitter of the transistor, is sending the signal back to the inverting input to be compared all the time with a fixed voltage appearing. This is why there is a Zener diode between R2 and the ground, because we want the two ends of the potentiometer to have access to a constant voltage regardless of the state of the battery or the power supply. And then you can adjust the signal at the non-inverting input from the wiper of the potentiometer. The rest are just very easy resistors to find everywhere, so there's nothing special about it. Now, what's interesting though is the presence of the two Zener diodes here. They have two purposes. I'm gonna tell you what is the most important is that when you connect the LEDs, even if you don't know the polarity of the diodes, if they have equal length for the terminals, if they conduct, everything is fine. But if you connect them opposite way, then the Zener diode is going to protect the LEDs against burning, because the reverse voltage of the LEDs is usually not higher than 5-6 volts. So by limiting that voltage to 4.7, the LEDs are going to remain safe. There's one circuit to play with, okay? And it's going to be this one. So this is the 100 kilo ohm potentiometer, and I have two LEDs pairing right now because they are the same color and they come from the same source. Now the second diagram is gonna be right here. This time, instead of having as reference a Zener like in the top diagram, just let me put the power supply. The power supply is exactly the same, 9 volt, R1, 6.8 kilo ohms. Instead of having a Zener diode here, you are going to have a red LED. We use it as reference. So the voltage should be somewhere around 1.6 volt, 1.6, 1.7. And now we're going to have operational amplifiers. Okay, and then we're going to have second one. Here is going to be the diode we want to test. Here we're going to have the famous, let's mark it in red, current sensing resistor. Very good. So then here we have the power supply. This is the pin 4 for the ground, sorry. Here is the pin 8 this time, which is the positive voltage. Now the pin numbers. This is another kind of circuit. I'm gonna put here just to make sure you get it, because of course you can find the specs for this package. Is this time LM358. It's a double op amp, as you can see, one op amp here and another one here. So if we put it here, LM358, This time the ground is on the pin 4, but the positive voltage is on the pin 8. So here on the pins 1, 2, and 3 you have the first op amp, and on the pins 5, 6, and 7 you have the second op amp. Okay? And there are two of them in the same package. Actually, they are very easy to connect. It's the package right here. Okay? Also 8 pins like the other one. And 5, 6, 7, and 8. And it's very cheap. It's something around $1. Okay? So for the rest, the potentiometer, let me just correct a little error here. Is not this one here. This is coming from the potentiometer. Okay? So the potentiometer P1 is around 5 kiloohms or 4.7. The original resistor here, R1, this is going to be R2. I'm going to put a note here. If R2 is about 56 ohms, you can manage the current adjusting from the potentiometer from 0 to 30 milliamps. I modified this one to 70 ohms, to around 70 ohms. I wanted to make it similar to that one. I forgot to tell you for this one here, the current into the LED, into the two LEDs in series is going to be approximately from 0 to 20 milliamps. I wanted to get something similar here. So when R2 goes to 70 ohms, so the current goes from 0 to about 20 milliamps. So it's going to be the same as the other one. So I'm going to start with this one here. Let's keep the diagram over here. And for this one here, if I'm going to connect the ammeter, we're going to connect the ammeter. Over here. We'll be able then to monitor what happens. So right now, if you watch this one, you can read here the current being about 10 milliamps. You take a look, the current goes 0, and now I can increase it, and if I go to the maximum, it is about 20 milliamps, almost 21. But you see the light here is very bright. If I want to pair this one with the other two LEDs existing there, I have to obviously lower the amperage. So I don't take a look at the amperage just yet. I'm taking a look at the brightness. So let's say something like that is going to give me a similar brightness to the other two ones. So at this moment, if I want to connect it into a circuit, I will know the current consumed by this LED for a good brightness to mount in a panel, so I'll be able to calculate the limiting resistor. Right here, if I make the calculation right now, let's suppose if you have a 5 volt supply and you connect the limiting resistor here and our diode, what we know is the current passing here for the series connection between the resistor and the LED is about 2.4 milliamps. Here the power supply is 5 volts. We want to know what is going to be the size of the resistor. For that, we need to know what is the voltage of the LED. Remember, we split these LEDs in two classes: red, yellow, green, amber. Standard LEDs, we consider the voltage to be around 2 volts when we do the calculation. The white and the blue, we consider the voltage 3 to 4.5 volts depending on the manufacturer. But right now, we can measure the voltage. We can measure the voltage across that LED. We take a look. So if we measure the voltage across the LED, 1.8 volts. So the voltage across the LED is around 1.8 volt. So the voltage across the resistor is going to be what? 5 volts minus 1.8, which is 3.2 volts. So then 3.2 volts is equivalent to 3200 millivolt. So the size of the resistor is going to be the voltage of the resistor over the current. The current into the resistor is going to be the same as the one into the LED. So 3200 millivolt over 2.4 milliamps. Very easy. We do the math. 3200 divided by 2.4, and we find a resistor of about approximately 1.3 kilo ohms. So if you connect that very bright LED at a 5 volt supply as the most of the TTL circuits, you are going to need a resistor about 1.3 kilo ohms in series with it. This is where it is interesting to understand how to play with the brightness of this one. Now let's go for the other circuit in the top. I'm going to disconnect the ammeter from here, even if I'm leaving the LED connected by shorting here the wire. And we are connecting now our multimeter, our ammeter, to monitor the current or the consumption into the circuit right here in the top, the diagram right here in the top, where the two LEDs are in series. So this is going to be the potentiometer. Take a look. If you take a look on the ammeter, now you have practically 0 milliamps consumption. So obvious you have 0 brightness. And then you can increase the brightness, and the maximum is going to be around 20 milliamps. So pretty similar to the other one. If you adjust it, if you take a look and you adjust it about 10 milliamps, the brightness is pretty nice. As you can see, the brightness is not as big as it was for the red LED. So for a similar brightness to the red LED, these ones need 10 milliamps instead of 2.4. So if we do the same calculation as before, and we want to know what's going to be the size of a resistor, of a limiting resistor, in a similar circuit having a power supply of 5 volts, if you connect only one, you don't need to connect both. If you only connect one of them, and you have the new LED here, the other one was red, this one is a kind of amber. You know the current here is now 10 milliamps. So you want to know, if you are having only one diode connected in a 5 volt supply, what would be the size of the resistor? We're going to need to take the same measurement. What is the voltage across one of these two LEDs? So we take the measurement. 1.98 is practically 2 volts. Remember about the voltage we use for calculation for these LEDs it was around 2 volts. Now it really is. So voltage across the LED is about 2 volt. Voltage of the resistor is 5 volt minus 2 is 3 volt, which is equivalent to 3000 millivolts, exactly as before. So the resistor is what? Is the voltage across the resistor over the current. So it's 3000 millivolt over 10 milliamps. Milli and milli, they go out. Volt over amps, it's giving me exactly the resistor in ohms. This time I don't need a pocket calculator. The 10 here cuts 1 0 from the top. So you need something around 300 ohms. Hey, take a look. There is a big difference between this and that. So this is where it's important to understand when you match the brightness for different LEDs, maybe not all of them, they need the same resistor. That was exactly the point of these diagrams. And what you can do, you have two choices. Either you can take a screenshot of this diagram right now. I hold it here for a couple of seconds. Okay. If you give me 1 second, I'm gonna clear the mismatch. Okay. So I'm gonna put here the diagram again for a couple of seconds so you can take a screenshot. Or I'm gonna also put a link to the source of these two diagrams so you can copy to see the originals and some comments. But these are exactly the two ones I just wired here for you. So far so good? Okay, I'm gonna take this one away. We don't need it anymore. So remember, what was the purpose? The purpose was to start playing with our digits. And now we know to play with the brightness. And then we pass to the next step, which is how to adjust the brightness for this one. Actually, in a real application, you don't need to modify the brightness of this one, but you have to know how to calculate the size of the limiting resistor for the digit. So for that purpose, I'm going to reconnect the power supply now. I'm going to keep the power supply connected over the digit, and we're going to measure the consumption by connecting our ammeter to the 7-segment display to see what does it mean playing with the brightness of it. Okay, very good. So we take a look. Right now, if I'm adjusting it to, we're very close to about 48 milliamps, you're going to count. All the lines, horizontal or vertical, are segments. So you count 1, 2, 3, 4, 5, 6, 7, and the decimal point, 8 segments. We have 8 LEDs. And the 8 LEDs, they consume right now 48 milliamps. By doing the math, it's very easy. All the LEDs are connected right now in parallel. So if I want to find the LED current only for one LED current, is going to be 48 milliamps consumed right now divided by 8, which is 6 milliamps. And my goal is to pair the brightness of this one to the brightness of the digits we're going to make our project next time. So then, in order to do this, let me figure here (8 milliamps, 10 milliamps, 15 milliamps and 20 milliamps. Because I have 8 LEDs, I'm going to need 8 times 8, 64 milliamps. For 10 milliamps per diode, I'm going to need 80 milliamps, because 80 divided by 8 is going to be 10. For 15 milliamps per diode, I'm going to need 120 milliamps total consumption to get 15 per diode. And finally, I'm going to need 160 milliamps to get 20 milliamps per diode. So we're going to do this to see what happens. Right now again, we have 6 milliamps per diode because the total consumption is 48. If I want to get 8 milliamps per diode, I'm going to shut the light off, and then we're going to modify the consumption to bring it to 64. So it's about something very close. It doesn't have to be exactly 64. Okay, something like that. So for 8 milliamps, you take a look, the consumption is pretty much the same as this one. I actually don't need to increase the consumption bigger than that, but just to show you what happens, I'm going to bring it now to 80 milliamps, because again, 80 milliamps is going to be 10 milliamps per segment. You need a fine adjustment for that. So it's going to be something like that. It doesn't increase significantly the brightness compared to this one. So you don't actually need, that's my answer, you don't actually need to increase the amperage through the digit, because it won't give you a significant increase for the brightness. Now I go for 120 milliamps. Remember, 120 milliamps is going to give you about 120 milliamps. It's very close. Okay. 120 milliamps is going to give you 15 milliamps per segment. Yes, maybe it's a bit brighter, but it doesn't worth the effort to make it 15 milliamps, almost the double, just for that. And finally, 160 milliamps. Take a look, 160 milliamps. And this is the brightness for 160 milliamps consumption. So what is my point here? Is that if you really want this brightness, which is good enough, take a look, it's absolutely good enough, it's very visible under the light. For your digits, you don't need to increase the consumption through the LEDs to 20 milliamps per segment. And we're going to measure here, keep in mind, we have now 20 milliamps per segment, and now we're going to measure the consumption for this one to find out what happens. Why the consumption of this one? Because, again, how many segments do we have here? 7 plus the 8 one, the decimal point. But if you count here, for the number 7, I have 1, 2, 3 segments. For the number 5, I have 1, 2, 3, 4, 5 segments. 3 segments here plus 5 there is making 8. So it's the same number of segments as one digit with all the segments on. So then, if I'm disconnecting the ammeter from here, let me just make it working, and I'm inserting this now over the power supply right here. Okay, I'm gonna connect this one. Take a look at the consumption right now. For all the 8 segments together, which are in parallel connected, I have 52.5 milliamps. If I do the math, 52.5 milliamps divided by 8 segments, I have a consumption of about 6.5 milliamps. That was exactly my point. So why to increase the consumption to 20 milliamps per segment when you can have it extremely visible with a consumption of 6.5 milliamps? So that's exactly the conclusion for today. Maintain the consumption low enough, but not to have it too dim, just to have it bright enough to be seen all the time, and not to increase it too much, because again we are going to see some integrated circuits controlling these digits. And we can limit the consumption in such a way that everybody's gonna feel comfortable. So far so good? So next time we're going to deal with numbers. Thank you very much. See you next time. Bye-bye.